So I want to talk about that first because he uses that in at least the first two chapters of his book. So first of all, you can open up Excel. We'll do it in R, but just to show you another way to do regression, we'll do it in R. So you can we'll do it in Excel. So you can open up Excel, and you can type in the following. Okay. So put that in your Excel spreadsheet. And then you need to, I want to access Excel's regression functions. And they're not available just here, so you have to add them in. Because if Excel put everything, when you open Excel, if it added everything in, it would use up a lot of memory. So they choose not to add everything, because most people don't use regression most of the time. So why should they load the memory with regression if you're not going to use it? So you have to add it in. So you go to File and Options. File and Options. And then you go down here to Add-ins. Add-ins on the left side here. And you click that. And you see this. And way down at the bottom of this page, it says Manage Excel Add-ins here. And you click Go. And here are some extra stuff that you can add in that don't normally add in by themselves in Excel. And the one that we want is called the Analysis Tool Pack. So you click that Analysis Tool Pack and click OK. And now I forgot to show you, but if we had clicked Data before, this one up here, this wouldn't have been there. Okay, but now it is. Okay? Okay, now we have two columns here. And the first column is called fertilizer, and the second column is called yield. And we're thinking of like a farmer who's planting something like rice, and he's testing to see how much fertilizer will improve his yield, his rice yield. Okay? So he's got, how many rows of data does he have? Like how many different fields does he have? It starts at 2 and goes to 14, so 13 different fields, right? So he's doing an experiment with 13 different fields. Okay? And the first thing we could do is we could plot this data. So why don't you do that? Plot this data and see what it looks like. And this is why in the first 2 chapters, before you plot it actually, this is why in the first 2 chapters he plots things, because plotting things helps you see very clearly some things that you may not see just by looking at this. And if this was really a lot of data, not just 13 rows, but say 15,000 rows, it would be really hard to see it. But plotting it will definitely improve your ability to understand what's going on. So, okay, why don't you plot it and see what you see? Find out what you see. So, how do you plot it, by the way? Somebody guide me through that? What? Insert. Okay, that's the one that I think works best, is the scatter. Okay, so just click on that and choose like this one, the first one. And you get this. Okay? So, what would you say already about whether fertilizer gives you better yield? What's the x-axis here? What's the x-axis on this graph? It's the fertilizer, right? And what's the y-axis? It's the yield. So what would you say? Does adding fertilizer improve your yield or not? If you were this farmer, would you decide to use fertilizer or would you not? If you wanted to increase your yield? You'd probably use it, right? Okay? So we can see from the picture something that we couldn't see very easily without. Like right now, I think most of us are very much in agreement about the fact that fertilizer does improve the yield. But if we looked at the original data, we may not be in such high agreement about it, or such clear agreement about it. Okay? All right, any questions about that? All right, now, what we'd like to get is an equation that says that the yield, let's call it that, yield is some function of fertilizer, right? I'd like to have a function like that. That would be great, right? Then I could tell what? If I know the fertilizer, I could give a prediction for the yield, right? Now, it's not clear whether this function should be a line or not, or if it should be a curve, right? Maybe the dots look like this, and you might think it could be a line through that, or you might think maybe there should be a curve through that, okay? But for now, we're just going to be talking about what's called linear regression. So we're going to try and find a line that fits this the best, okay? Does everyone understand? Okay, so we can do that with Excel quite quickly and easily since we loaded in that package. And so you just go back to data here. And actually you can delete this graph. Excel will give you a different graph. Data analysis will give you a different graph. Anyway, just go back to data and click on data analysis here. And there's a bunch of things that functionality that they give us, but the one we want to work with is called regression. You select regression. Now, okay. Or before you do that, okay, so does everyone understand what we want to do? All right, let me talk a little bit about this PowerPoint, which is about regression, and then we'll go and finish it up in Excel, and then we'll do it in R. So this is called simple linear regression. So the fact that I just explained what we mean by linear. So what do we mean by linear here? What do you mean by linear? We're going to try and fit a straight line to this data. Okay? And simple means that we don't have more than one variable as input. We just have one input variable. But that's a very simplified scenario, right? Usually, yield is going to depend on much more than just fertilizer, right? And when we do data mining, the whole point of data mining is to be, one of the main points of data mining is to be able to deal with many, many, many variables, like 1,000 variables, 1,000 input variables, okay? So, so we're going to start out with what's called simple, though, and linear regression. Now, when we do data mining, we're not stuck with linear either. We have all kinds of flexibility, which that's another power of data mining, is that you don't have to just do linear, you can do all kinds of things that are definitely not linear. So you can see from the picture that I drew up there that linear is going to limit you in terms of the trying to fit to the data, right? So, but let's look at it anyway. Okay, so here's another question. Are the heights and weights of persons related? What do you think? Are people's heights and weights related? Just like we just said, is yield and fertilizer amount related? Yeah, right? And heights and weights are also related. Does a person's weight depend on his or her height? Now, that is, obviously, it's not a perfect relationship. That is, if you know somebody's weight, you can't tell exactly how tall they are, or vice versa, right? But generally speaking, the taller someone is, the more they're going to weigh, right? If yes, what is the change in the weight of a person on average for every 1 inch increase in height? So in other words, if you can know, see, the key word here is on average. So they're not being, they're not saying it has to follow perfectly, right? But then we would still like to know on average. So we don't expect it to be perfect, but on average, if you know that someone is an inch taller, how much more weight would you predict that they have? Okay, you don't expect to be perfect in your prediction, but we still can ask the question and give an answer. Okay? Okay, so, yeah, I was afraid of that. Okay, sorry about it. Okay, so bring back to this. Okay, so what is the rate of change for the National Basketball Association players? So a specific set of people. Okay, so simple regression and linear regression we want to talk about. Definition. A regression model is a mathematical equation that describes the relationship between two or more variables. So what I said is that we want to find a relationship between yield and fertilizer, and we want a linear relationship. That means we want a linear equation that relates yield to fertilizer, right? Okay. So a simple regression model includes only two variables, that's what I said, one independent and one dependent. What's the dependent variable in the example that we just talked about? The dependent, I'm sorry, what's the independent variable? The independent variable is the one that goes in the function, and the dependent variable is the one that comes out. So what's the independent variable? Fertilizer is independent, and we say that yield depends on fertilizer amount, right? So that's called, the yield would be called the dependent variable in this scenario. The dependent variable is the one being explained, and the independent variable is the one used to explain. And they say to explain the variation in the dependent variable. Now that always bothered me. I didn't quite know what they meant by that. I puzzled over it. And I think for most people it's probably clear, but for me it wasn't. But what they mean by explain the variation is that yield varies, right? The yield varies, right? But we're asking why does it vary? And we're suggesting that the reason is, one of the reasons is that there's a different amount of fertilizer, right? That affects the variation. Okay, definition: a simple regression model that gives a straight line relationship between two variables is called linear regression model. Okay? Okay, so here's a picture of a linear regression model that, and what are the two variables that they're relating here? What are the two variables that are being related? Income versus food expenditure. So if somebody's income increases, what would you say? If you get richer, what happens to the amount of money you might spend on food? Goes up. Maybe not the amount of food, but maybe the quality, or you might start buying fancier things or something like that, right? So as your income increases, your food expenditure may increase. The left side graph versus the right side graph, the difference is what? One, we're saying that there's a straight line relationship, and one we're saying, no, it's not straight line, it's some other curved relationship or nonlinear relationship. Okay, now here we have some actual numbers, right? We have 5, 10, 15, and so on. I don't know, maybe this is money. Maybe this is $5,000, $10,000, $15,000. And maybe this is amount of money spent per week, per month, or whatever. What?
It's a lot of money.
For a week, yeah. But maybe not for a month. Or maybe, no, it's not a lot for a month. Okay, so, what's the x and y coordinates of this point right here? What are the x and y coordinates of this point right here? 0, 50, and how about this point right here? 10, 100. So from that, we can figure out the slope of this line. Right? We have 2 points on the line, we can get the slope. Okay? And from that, we can also get the equation of the line, right? If you have 2 points, you should be able to figure out the equation of the line, right? So simple algebra. Okay? So it turns out that the equation for this line is this. So what's the slope? 5, right? According to this equation, it's 5. Let's verify that it actually is 5. How do we verify it? We take 100 minus 50, which is 50. We take 10 minus 0, which is 10. We end up with 50 over 10, which is 5. Okay, so the slope is 5 and the y-intercept is 50. Okay, everyone remembers that? And the change, so here we have, if we move in this direction by 1, the fact that the slope is 5 means that when we move, oh God, what happened to this thing? Why does this not show up? It's on automatic. Okay, so as I move in this direction by 1, how much do I move in this direction? 5, right? That's what the slope means. Okay, so if we have a change in x of 1, we get a. Why is it doing that? I must have the wrong option here. Visible, okay. If we have a change in x of 1, we get a change in y of 5, and that's going to happen everywhere because this is a straight line. Okay, so we have scatter diagrams, we have what's called the least squares line, we have the interpretation of A and B, that means that A and B mean this. This is called B usually. Wait, no, sorry. This is called B, I think, and this is called A. Well, we'll see what they're going to call A and B. Okay, and the assumptions of the regression model. Okay, so for a simple linear regression model, the equation is going to be a linear equation, and this is the example of a linear equation, and A is the intercept, and B is the slope. Okay, everyone agree with that? Okay. In the regression model, y equals a plus bx plus epsilon. Now, what is that? Why do they put that epsilon in there? Because here's the data, for example. Where's the line? Let's say the line is there. Okay? That's the line and the data. Why do they put that epsilon in there? So without the epsilon, we're talking about the equation for that line. Okay? With the epsilon, we're talking about the data points. In other words, the epsilon means that we expect that there's some error or some difference between the actual data and the regression line. Is that clear? Clear or not clear?
You mean this one is away from the line?
Yeah, exactly. It means, epsilon means that if we don't have the epsilon, what is this? If I draw this, what does it look like? A straight line, right? So that's this, if we don't have the epsilon, we're talking about the straight line. Okay? But they put in the epsilon means that it means error off of the line. What we're saying is, yeah, we think that the relationship between y and x is linear, but we don't expect it to be perfect. So we expect that there's some error off of the line, and so they throw in this extra term, epsilon, to represent the fact that it could be plus or minus a certain amount. And that epsilon can vary. For each term, it'll be a little bit different. I'm sorry, for each dot, it will be a little bit different. Okay, is this clear? Okay, good. And so, I don't understand. I thought I did this right. No? Please don't turn on log on your computers. Okay? Why doesn't it work? I think I didn't work. Okay, can you keep your hands off of the mouse? Can you take your hands away from your mouse? Like this here. Now my hand is on the mouse. Now it's not. Okay? Okay. So, all right. So is this clear what the epsilon means? So the epsilon is like an error term. We're saying we don't expect it to be exactly on the straight line. Okay? In the regression model, this is called the regression model. A is called the y-intercept. This term here is called the y-intercept, or constant term. B is called the slope, and epsilon is the random error term. The dependent and independent variables are y and x respectively. So this is the dependent, and this is the what? X is the independent variable. Okay? Now, they have another term here, another symbol here. This one. Now, does this equation have the epsilon in it? No. So what's this is always going to give me what? There's no error term here, right? Okay, the y hat refers to the predicted value as opposed to the actual value. Okay, let me show you that. What's here, the y, is this y going to give me the predicted value or the actual value? The actual, right? That's why we included the epsilon, so that we could basically say that y is the actual value. On the other hand, is this just this part here, without the epsilon, is that going to give you a predicted value or the actual data point value? It's going to give you a predicted value. So the y hat is the predicted value versus the y is what? the actual value. Okay, so they always use that in statistics. They always use y hat to stand for the predicted value and y to stand for the actual value. Okay, so the actual value for data point, like here's a data point, 55, comma, 14. So this 14 would be a y, not a predicted value. This is an actual data point. Okay, I don't know if I'm making sense or not, but I hope so. Okay, so is this clear what the y hat is? Okay, so in this model, now, okay, should I call this the model, or should I call, which would it be a better use of the word model? Here, or this one? Actually, they call it this, they also call this the model. Okay, so I won't make that, I won't insist on that. Okay. Okay, so here's our data, right? We have how many rows of data do we have here? How many rows of data? 7 rows, right? So that means 7 points, right? 7 points in the graph, right? So if I look at the graph here, there are 7 points. Is that right? Yeah, there are 7 points. Okay? So, definition. A plot of paired observations is called a scatter diagram. Okay, so you already did the scatter diagram, and this is the scatter diagram, right? That's called a scatter diagram. And each one of these dots represents a household, right? Does everyone agree with that? Each one of these dots represents a household, right? How many households do we have? 7. Each household has an income and a food expenditure associated with them. And we can plot each household in this income food expenditure plane. Right? We can plot each household in the income food expenditure plane. And this is what it looks like. All right, now the question is, which line is the best fit? Once we decide on the line, then we'll be able to say, okay, if you increase income by 10, you can expect food expenditure to increase by such and such. But the question is, which line should we use? Right? So how do we decide on a single line? Because we want only one line. We don't want to say, there's 10 different lines. Right? We just want one line. So how do we decide which line to use? Okay, what? Yeah? What did he say?
The line which covers the most number of dots, the points.
Okay, so we have 2 different answers here. One person said the line which goes through the greatest number of dots. That's a good one. I like that. That's one criteria we could use. And then another person said, what did you say?
The one with the least amount of errors.
Yeah, he said the one with the least amount of so-called errors from that line to the dots, right? So here, there's this dot has this much error from this line, right? And here, this dot has just a tiny bit of error from this line. And this dot has a certain amount of error from this line, right? So we could say, which line has the least amount of error from the dot, right? Does everyone agree with that? So those are 2 good criteria. I like both of them. So which one should we use? So everyone understand that first suggestion was the line which goes through the most number of points. So like, I guess maybe this line goes through 2 points, and this line only goes through 1 point, and this only goes through 1 point, and this line goes through 2, right? I don't know, right? That's a good criteria, but that isn't the one that they use. But I think that's an obvious choice. But it's not the one that they use. They use the one, they say the one that has the least error off of it. Okay? The one that has the least error off of it. Okay? So for example, this line there's this much error for this dot, and there's this much error for this dot, and there's this much error for this dot, and so on, right? So we could look at the error for each, that we could sum up the error for each line and see what, and choose the line which has the least error. Okay? Everyone understand that? Any questions? Okay. And the only problem with that method is that when you do the summing up, are we gonna call this a positive error or a negative error? This one here. Probably a positive error. And then what are we gonna call this one? Probably a negative error, negative, negative, positive, positive, negative, right? Now, what do you think could happen when you add these all up? Since you have negatives and positives, you could get 0. In fact, most lines that you use, you will get 0. So if you sum up the errors, and you're doing this to try and choose the line which has the least errors, and you get all of these with 0, it doesn't help you, right? So we have to do something slightly different than that, and the obvious thing to do is to get rid of the negative signs. Just make everything positive, and then sum it up, and then you could do it, right? Then you could choose between one line and another, right? So you could do it that way, but actually they do it this way. Now this looks messy, but you know what the sigma sign means, right? Just means add up. So your idea was to add up all the errors, but instead of, and then the alternative to that was to make all the errors positive, and then add them up. But what they actually do instead of making them positive is they square them, and then add them up. Okay, does that make sense? Now, how do they express error in this equation? Obviously, it's y minus y hat. Now, why is that the error? Why is that the correct expression of error? Because what does y stand for and what does y hat stand for? Y stands for the actual value, and y hat stands for the predicted value. And the predicted value is where? It's the point on the line, right? And the actual value is the dot. So this is exactly the right expression for the error, right? Okay, so we do that. And what is this? And this is called the error sum of squares. And this gives you an estimate for regression. Do I have to go into more than this? Maybe not. Okay, here, because of calculus, you can show that, remember, what are we trying to find? We're trying to find the line, right? When we say try to find the line, I mean, I don't want you to try and point to it in the graph. That's not clear enough, right? What do I really want when I want to describe the line? I don't want somebody to say, oh, I think the line is here, right? And put their hand there. That's not really very good, right? What do I really want when I want to identify the line? I want the slope and the y-intercept, right? Right? So this gives you the equation for a and b. What b was I forget, b is what? B is the slope, right? B is the slope, so this is the equation for b, and this is the equation for a. And these you can calculate. This basically is like the sum of squares, but it's slightly modified. But anyway, through calculus you can calculate, or through these equations are derived from calculus, you can figure out what a and b are. Okay? Everyone understand that? Okay. And you can look at this later. So we don't need to do that. So let's let Excel do the calculations for us. Oh, but you already, I had to shut down your. Okay, you can watch me. Okay, so you bring in regression, and you have to tell it what's the x variable and what's the y variable. What's the input variable, x variable, and the y variable. So what's the input variable in this example? Fertilizer, right? So I do this. Okay, and what's the output variable? Yield, so I do that. And you have to say that you included A1 and B1. So you have to say you included the labels in there, otherwise it will get confused. And then you can also say, I want to see a picture of this. But what we're really after is the A and the B. Okay, what we're really after is the A and the B. But we'll look at the picture also. So, or not the residual plots, I'm sorry, the line fit plots here. And that's it. And you just click OK. And there it is. Okay, so here's the picture. But as I said, what we really want is the A and the B. We want the equation, and the A and the B are here. Are there. Okay, so the intercept is so the equation is going to be y equals, equals the intercept, I want A, what do I want? The intercept first, so I'll say 1015 plus, no, that doesn't work either. I should do this. Plus 8, I'll just round it up to 8 times what? X. Let me just do this here. Okay, so everyone see the equation? So the regression equation is y equals 1000 plus 8x. Okay, so Excel gave us the y-intercept and the slope. Okay, and that's where it gives it to you right here. The other stuff is more statistical stuff. We don't need to go into that. And here's the actual picture. Now this is supposed to be, sorry, let's see, make it smaller and bring this down. Here, make it bigger again. Okay, so what's the y-intercept of this? So the blue dots are what? Are they the predictions or the actual data? The actual data. The red squares are what? Those are the predictions, so that's our regression line. And the y-intercept of this regression line should be what, approximately? 115, right? I'm sorry, 1015, which is maybe what it is, right? Maybe this is 1015. And the slope is supposed to be what? About 8, right? Okay, any questions about that? What's the interpretation of the 115 and the 8? What's the interpretation of the 115? What does that mean? That's the y-intercept, so what does that mean? That means if you use how much fertilizer? That's over here, right? So what does that mean? If you use 0 fertilizer, how much yield do you expect to get? 1015, whatever it is, bushels or something, right? Okay? And what's the interpretation of the 8? What's the interpretation of the 8? What does 8 mean? That's the slope, right? So what's the interpretation of the slope in this picture? What's the x-axis again? Fertilizer. And what's the y-axis again? Yield. So what's the interpretation of the slope being 8?
Every amount of fertilizer.
Yeah, for every unit of fertilizer that you increase, if you increase the fertilizer by 1 unit, you get an increase of 8 units in the yield. So if fertilizer is really expensive, maybe it's not worth using it, right? If you only get an increase of 8. But it depends on the cost of fertilizer, right? Right? If fertilizer is cheap, then it might be worth it, right? So, but anyway, the interpretation is what? If you increase fertilizer by 1, whatever it is, maybe it's 1 kilogram, then you get an increase of 1 bushel or something. I'm sorry, 8 bushels of yield, right? And so on. Okay, does this make sense? Everyone understands? So this is called, what is this called again? This whole technique, this whole model, what? Called regression. And specifically, how many variables did we have for input variables? No, for input variable, 1. And what was that input variable? Fertilizer. So 1 input variable, and are we looking for a curved relationship in this example? No, we're looking for a straight line. So this is called regression, but it's specifically what kind of regression? Simple linear regression. Simple means 1 input variable, and linear means we're looking for a straight line. Okay? So we've done that now in Excel, and we've covered regression in Excel. Okay? Okay, so you're familiar with regression. Now R certainly can do regression as well. You don't have to go into Excel to do it. If you have a column of data for, so how would we load this data into R? How would we get this into R?
Save as
What?
CSV.
Sorry?
Save as CSV.
We could save it as a CSV file and load it in that way. Or if you wanted to type it, how would you do it? Sorry, a vector. What would you call one of the vectors? What? Fertilizer. And then you'd have type, and you'd enter that in, right, as a vector of numbers, right? And then what? Yield as a second vector, and then what? Yeah, matrix, it would work with matrix, but typically we use what structure? Almost always, no, and almost always we want to use a data frame. Okay, I'd say 98% of the time, 99% of the time, it's going to be a data frame. Okay, so how would you create a data frame from this? So here, to create a list, what did we use? List. So what's the function for data frame? Data.frame. Okay? So you just do the same thing as we had list, and then you'd have, but it would be data.frame, fertilizer, comma, yield. Right? Okay? And then you'd have your data frame. You could have called it my data frame or something like that. And then you could try to do regression in R. And you'll get the same sorts of results. Okay? So we want to be able to do that. Okay, is this clear? Okay, so now, before we, we should go now to, actually I made a bunch of videos for graphing, but I guess I'll go through it now. We can go through it together instead of the videos, and then if you want to review it, you can check the videos. Okay, so now you can log on. And let's go to R, and also let me go to the book. Okay, so this is chapter 3 in R in Action. And so try this out and see what happens. First of all, what do you think is going to happen here? What is this going to do? Sorry? Oh, it was what?
There must be some kind of file called ntcars, surely.
Right. Actually, before you do this one, just type empty cars, or type head empty cars. So what do you get? It looks like a data frame. In fact, I also type STR empty cars. Find the structure of empty cars. What is it? What kind of thing is this? It's a data frame, right? And then it tells you how many fields are there. What are the fields? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 fields, right? And what are these fields about? Obviously, miles per gallon, cylinders, and so on, right? So it's something about cars, right? Okay, and then here we have the type of cars as well. So Mazda, Datsun, Hornet, blah, blah, blah. These are older cars, I guess, right? Okay, does everyone understand? Now, I don't know if you can see, but the first, well, you can see here, the first column is what? Here. What's the first column? Miles per gallon. It's not the name of the car. Okay? So there's an extra feature here, which is the row name. So the row names contain the title of the car. Okay? It's not part of the data set, actually. Okay? In a sense. Okay? The data set starts with miles per gallon. Okay? All right. So now, take a look at this and type it. Or, no, sorry. Now, what do you think this is going to do before you do it? So maybe we did we cover attach yet? Oh, okay. Attach, just just type this by itself. See what happens. Type plot WT, comma MPG, and like that. What happens? Anything?
I already did attach, so
Oh, without that, I mean.
I don't know.
Okay, let me try it.
I already
Let's see what I get. Did you get the same? Why do we get that? What does that say? It says error in our plot command. What was it? What's the error? What's the description of this error? It can't find what? WT. It doesn't know what WT is. So how can we fix that? What would be before you saw this the code that I just showed you, how would you fix it? How would you correct this error? Huh? How would you do it?
bring the file into R.
No, the file's already there. We already saw that we have the head and we have the structure. So it's already there. But no, I think what you would have eventually tried to do is this. Oops. For that, something wrong with my screen. It's not, doesn't look right. But anyway, and then here maybe. Like that, right? Now, it works. Okay? All right, everyone understand? But they didn't do it that way here. They didn't, I don't see, it doesn't say that, does it? Right? So this is an alternative way to do it. This way, you don't have to keep typing that empty cars $sign. So you might be wanting to use empty cars $sign many, many times. So this way you don't have to keep typing it. So what you do is you attach empty cars, And then you can refer to the variables without the empty cars $ in the front. Okay? All right, so now what do you think this is going to do? Well, oh, sorry, you don't know what it's going to do because you don't know what this does. So let's just type this. Well, no, sorry. All right, type attach empty cars and plot it just to see what it looks like. And then the next thing is don't do the AB line, just do what I have highlighted in blue and see what that does. And I'll give you one thing, tell you one thing, and that is LM stands for linear model.
Where is the tilde key on the keyboard?
That's a good, oh, I think it's all the way on the left top key. Is it or not?
Yeah, if you shift it.
Yeah, shift it, I'm sorry. Right. Okay, the tilde is left top key shifted. So I'm telling you that LM stands for linear model, and I'm telling you something else, and that is that Excel, this does exactly what we were doing in Excel. In other words, linear model means regression model. Linear regression model. Okay? So this does what Excel did. So let me do it. I'll cheat because I have to do it quickly because you're ahead of me. Each time I ask you to do it, you get ahead of me, so I don't have to type it. Oh, what is wrong with this? Things wrong. Okay, and then do this. Now, what do you think is the y variable when I type this? And what do you think is is this what it said? Let's see, what did it tell us to do? Yeah.
The other way around.
Okay. No, that's what it said.
Oh.
WT is first.
Oh, yeah.
Oh, no, you're right. I'm sorry. You're right. I apologize. MPG tilde WT. Something wrong with that, isn't there? My pointer is pointing at the wrong place. Okay, so what do you think is the output variable here? What are we trying to predict? So in the Excel example, we were trying to predict yield from fertilizer. Here, we're trying to predict miles per gallon based on what variable? The weight. Okay, so what do you expect to happen as the weight increases? What happens to the miles per gallon?
It'll be a negative probably.
Yeah, you expect it to decrease, right? As the weight increases, you expect the miles per gallon to decrease. Now, we already did the plot over here, and this is the picture of it. Okay? Right? You did the plot yourself, I think. Yeah. So this is the picture of it, right? So what's the relationship between weight and miles per gallon? As weight increases, what happens to miles per gallon? It decreases, right? Now, what do we want to get next here? We want to get a line that fits this data best, right? I want to find the line that fits this data the best, right? And the way that you do that in R, not in Excel we just saw how to do it. In R, you do this, LM. And you put the y variable first, and then the input variable next. And you separate by tilde. Okay, so what do we get when we do that? We get that. So first of all, what it says is it's using this this function. So, okay, well, that's fairly clear. And then it tells me the coefficients, just like Excel told us the coefficients. Remember, I highlighted the coefficients in yellow in Excel. Can't get it now. How can I see it? Where is it? Here. Remember, I highlighted them in yellow? Those were the coefficients. Now, so now I have the coefficients as well. So what is the slope? Should the slope be positive or negative? Negative. As weight increases, miles per gallon decreases. So the slope should be negative. And what's the actual number? About -5 or -5.3. And what's the interpretation of that? In other words, remember when we said for yield and fertilizer, as you increase the fertilizer by a certain amount, you get 8. If you increase fertilizer by 1, you get an increase of 8 in the yield. Now what's this -5.3 mean?
Increase the weight by,
As you increase the weight by 1, you get a decrease in miles per gallon of 5.3. So it must be bigger than just 1. It must be like 1,000 or something. It depends on the units that they were using, but it must be like 1,000, or I don't know. Anyway, that's what we get, right? Okay, is this clear? And what's the intercept mean? Well, we already talked about what the intercept means, right? Okay, so any questions about this? Okay, now before you run it, what do you think this might do? Now, this is not exactly clear, but what do you think this might do? It's going to plot a line. And what line is it going to plot? The regression line. And what line is that? That's the line that we just saw with the slope was what? Slope was -5.3, and the y-intercept was 37, right? So it's going to plot that line. So let's try that. And look at it, and there it is. Okay, so that's kind of a cute way to get the regression line, right? We've used AB line before, right? But for AB line, typically, you need to express the A and B, right? You need to say the slope and the intercept when you use AB, right? Or sometimes we use AB line like this. How about this? What does this mean? Remember? That will draw a vertical line at horizontal line at 5. And if you wanted, you could do this, and that would draw a vertical line at 5. Okay? But if you want to get I forget, what was it? AB line, I think it's A. A is what? Is A the slope or I can't remember. One of them's the slope and one of them's the intercept. B is the what? Slope? Okay, so if I did this, 10, 3, then what? It would draw a line with y-intercept of 10 and slope of 3, right? But here we can do it we don't have to express the slope in the inner line. If we just put in the linear model, it calculates the linear model, extracts the A and B, and plots them. Okay? Is that clear? Okay. Okay, now let's look at the next piece of code. Okay, now do this one. Or you can just type something. You don't have to type that whole thing out if you don't want to. But do a title, and don't forget the quotes. Give it some title. Okay, you don't have to do that title, but some title, so you can add a title this way. Okay, and now we detach cars. I think when you attach cars, you're kind of storing it in memory, and so it's better to get rid of it when you're finished with it, and also so that when you refer to WT, you may not mean about the empty cars database later. So you want to delete that basically, get rid of that. So you detach like that. Okay, so now if you refer to empty cars, if you refer to WT again, then it will give you an error. Okay, because it doesn't know after you detach. Okay, is this clear? How this works so far? Now, what this will do is everything that you did here you can store it in a PDF file. You can store the results in a PDF file. All you have to do is put PDF and the name of give the file a name, and then at the end say, okay, I'm finished. So just store all of that in one PDF file. So try that. So first type PDF and give it a name, like something.pdf. Don't forget the quotes. And then you can just use your up arrow key to get these, so you don't have to retype everything. And then dev off at the end. Dev dot off at the end. So let's try that. That was the next one. Okay, so now check and see if you actually created that. So it might be in maybe in documents. Yeah. Okay, because that's your working directory. And if you check it, you get that. Okay, so you can save your pictures. And you can also do it this way though. You can also just click on the picture, right click and copy it as a bitmap for it and paste it somewhere if you want. Okay? Okay, let's go on. Instead of making it into a PDF file, he says you can also make it into a bitmap file or some of these other formats as well. Okay, PNG, a JPEG, and so on. Okay, and then he says you can do some other stuff as well. Now, he says, creating a new graph by issuing high-level plotting command, such as plot or hist or boxplot. By the way, let's try hist. Try hist and weight. So make a histogram for the weight variable. Okay, try and do that. Make a histogram for the weight variable. So the command is HIST. So I expect some of you to make an error the first time. What? Yeah, you need to reattach it, or you can refer to it with the $sign notation. Okay, do you get it? Do you get something now? So I won't reattach it, I'll just do it this way. Okay, I did that, and I get a histogram. Okay, is that clear? And if you wanted to save that, you could. Now, he also says, though, that creating a new graph by issuing a high-level plotting command such as plot, hist, or boxplot will typically overwrite a previous graph. So if you go, if I check R now, I have this, but I lost my previous plot. Okay? So how can you avoid losing it? You can do this. So you do dev.new first, and then you plot something, then you do dev.new second, and then you plot something else, and that way, so try that. Try, so we already have one, well, no. So try dev.new. So I guess dev.new gives me a blank screen. And then hist, for example, you have to click back in R, because it shifts the focus back to to the plot. So then this, and then do dev.new again, and then some other graph. Oops, didn't work. Okay, so now, hopefully, if I go to the windows here, I have both. Okay, so I have this one, and I have this one, same one, and I have this one. Okay, so you don't keep you overriding that way, if you want to. Okay, so you can use this dev.new command for that. Any questions about that? Okay, now we have some data like this. And this is about in a medical experiment where they're testing their responses to two different drugs, drug A and drug B, and they're giving the same dosage for each of the drugs and then testing, I guess on different people maybe, but they give a 20 amount of 20 as a dose and see what the response is like. Maybe this is blood pressure, or not blood pressure, that's pretty low for blood pressure. But maybe this is, I don't know, like something in somebody's blood, an amount of something, an amount of some chemical in somebody's blood or something like that. So if they do drug A, they see that the amount is 16. If they use drug B, they see the amount is 15. And then they increase the drug dosage to 30, and the amount in A, if you use A, is 20, and 18, and so on, right? Okay, so we have some data. So you can input this data using this code, right? And then then we can plot like this, right? Okay, now let's do that. We don't really have time. Okay, watch, I'll do it, because we don't have time. So let's see, if I do this, so I'll input the data, like that, define these vectors, these variables, and then if I do this, now, we haven't seen that, we saw the plot function already. By the way, I'm sorry, they call the plot function, they call the HIST, the histogram function, they call them high-level graphing functions. High-level, as opposed to like the AB line function, which doesn't work unless you already have a plot existing. Okay? So we'll draw a line, but you have to have a plot open already. Okay, so that's not a high-level one. So a high-level one creates the plotting graph, and then you can do other stuff after that. Okay, so anyway, I could do this, and so we saw the plot function already, but we never used the type B. Okay, so you can see what it does, and this is what it does. So type B refers to, no, I forgot. Okay, anyway, but I wanted you to check the plot function, the help for the plot function. Now, I don't know if you've been using the books method for checking help, So they tell you to do, if you want to check the plot function using, getting help for that, how do you do it? The book says do this. No. The book says do this. Whoops. What's wrong? Oh, I still didn't do it right. No, sorry. I didn't spell it. Okay, so the book says to do that, but you can also do it this way, if you want. Like that, so you can do it either way. That brings up the help page. And so what does type do? So check it out and see if we can find type. Oops, sorry, I did the wrong thing, didn't I? I did help on help. That wasn't right. On help on plot. Okay, so look for type, and here's what you get. Okay? So you can see that type for B is whether you want to draw the line or the points or both. So B stands for both, means you want both the lines and the points. So you could try just with P. I'll try just with P. And see what the difference is. Whoops, I can't seem to type today. Something's wrong with something's wrong with this computer. Right. So if I just want P, can I do this? That right? Okay, P. Okay. So now I just get the points. Okay? All right, that's all we have time for today. So, all right, we covered basic regression. You saw how to run regression in Excel and in R. Okay? And next time, I'm going to assign you to go through the chapter 3 in R in Action for homework, which we've been going through now, and you will learn all the details about drawing graphs. And then in class, we're going to go through chapters 1 and 2 in this book. Okay, so we're going to do some data mining through R, some exploration of data with R, but you should be familiar with graphing techniques because in his code, he does a lot of graphing, and so you should be comfortable at least, being able to read what he does. Okay? All right. So, and we'll have as I said, we'll have a midterm exam 1 week after the quarter exams. Okay?